Okay, so we can do one of these Heliox problems as an example of how this works. So we have a 6-liter tank at 3.56 degrees C. It's filled with 3.07 grams of carbon dioxide gas, 17.4 grams of chlorine pentafluoride gas. You can assume both gases behave as ideal gases under these conditions, which is important because hopefully we get to that today. So calculate the mole fraction and partial pressure of each gas. So we want the mole fraction of CO2, mole fraction of chlorine pentafluoride, and we want the partial pressure of CO2, the partial pressure of chlorine pentafluoride. And we want the total pressure in the tank. There's a few things that we can start with. What? Yeah, we want to get stuff into moles, right? If we're looking for a mole fraction, we have to have moles to calculate mole fraction. If I want carbon dioxide, it's in grams. So it's pretty easy to convert into moles. Carbon dioxide is going to be 12.01, 16.00. CO, there's 1 and 2. 44.01 grams per mole. So if I want to know how many moles of carbon dioxide I have, that's 3.07 grams of carbon dioxide. How do I get moles from grams? Divide by the molar mass, because grams then ends up on the bottom, 1 mole on top. So 3.07, 3.07 divided by 44.01. But yeah, cool, my calculator's in scientific mode. So 0.069756. Again, keeping more decimals than we need to avoid rounding errors. Okay, so that's moles of CO2. Moles of chlorine pentafluoride. Chlorine's 35.45. Fluorine is 18.99. 18.998. So realistically, you probably could have used 19. I don't know that one off the top of my head. 30.44 grams per mole chlorine pentafluoride. So we do similar things, 17.4 grams, and then divide by that. 1,3,3,3,9,4,6. Now we got moles. So how do I find the mole fraction? Yeah, so we need the total moles if we want mole fraction, because mole fraction is the fraction of the total moles, that is either CO2 or chlorine pentafluoride. So add those together. So that plus that. So total moles, I guess I could have written N total, is 0.2031 moles. So now we need to take the CO2. Yep. CO2 divided by the total, and then the fluorine, or chlorine pentafluoride. This is where it's really convenient. Learn how to save things in your calculator. 34337. And actually, this is a final answer. So 343, I guess we have 3 sig figs. So 343. Ooh, what are the units of mole fraction? It's unitless. So I guess you could think of it as, yeah, the moles cancel out, but the other part doesn't. So it's CO2 to total moles. But this would be our mole fraction. Let's write it this way. It's the mole fraction of CO2. 946,657. You could. I was actually going to point that out. So you could just say, okay, I've got two gases. So that's if you have two gases, right? I only have two gases. So if this is the fraction that's CO2, the rest of it should be chlorine pentafluoride. And then 1 would be all of it, right? This is the fraction out of 1 that is each gas. So you could subtract it and you get actually exactly the same thing. Sometimes you end up with slightly different numbers because of rounding or depending on how it rounds. So that's that. And then this one I can duplicate and it can go up there. Okay, so we found our mole fractions, but we still need the partial pressure of CO2, the partial pressure of chlorine pentafluoride, the total pressure. And I think there's multiple ways you could approach this.
You're going to give it the B equal nRT divided by, wait,
Divided by V?
yeah, divided by V.
For what though? What?
For the mole, you're going to use the total mole. You're going to, the R is 0.082. K with the Celsius that was given to you by 1% of 3.15 plus the volume, which is 6.
6 liters. It's already in liters. Yeah, I just meant total moles, but yes, all of those things are also correct. The total moles, if I use this number of moles, that will give me the total pressure. If I use the moles of CO2, that'll give me the pressure of CO2. If I use the moles of carbon, or I keep saying carbon, chlorine pentafluoride, that will give me the pressure of chlorine pentafluoride. So just starting with each number of moles, and then because they're all in the same tank, they're all the same temperature and same volume. So let's do that. So it's the ideal gas law, slightly rearranged, and let's do just the P pressure total first. So it's going to be 0.20318206. That's atmosphere liters per mole Kelvin. 3.56 plus 273.15. Yeah, just don't make mistakes.
Yeah, that's so helpful. Thank you.
You're welcome. So glad to help. Hardly. So pressure total equals 0.7688, although I'm going to write out the whole thing here. 5. What units will that give me? Pressure in. Why is it atmospheres? 0.08206. I didn't write the units in here, but is atmospheres, liters, mole, Kelvin. Atmospheres is the pressure part of that, so I'm going to get atmospheres as my volume. So this is total pressure is atmospheres. Okay. So the reason I left that without rounding it, and I could write it up here rounded, 0.769. So like I said, there's multiple ways you could solve this. I have the moles of chlorine pentafluoride, I have the moles of carbon dioxide. I could use those to find the moles of each of those gases. But that means that I've got to write out PV equals nRT again, solve it for P, plug in all of these numbers over again, type all of them into my calculator, and many more places to make a mistake. What's a faster way that we could calculate the pressures? Close, very close. Multiply it by the pressure total, because the pressure of CO2 is going to be the mole fraction times the total pressure, because the number of moles is what causes that gas to have pressure in the first place. So that fraction of total moles is also the fraction of the pressure. So I can take 0.7682. So this is my pressure total. I'm going to multiply it by mole fraction of CO2 first. And that should give me the pressure of CO2. And the mole fraction, I guess I used the rounded one there, 0.343. I don't have to recalculate it. When you're doing these for Alex, you should definitely use the whole number because it might get you on a rounding error. 2,6. And then over here, it's the same thing for chlorine pentafluoride. And that mole fraction was 0.657436. It looks like we... Oh, hold on. I never said I don't make mistakes. There you go. 505. I multiplied by 0.567. I'll go back down in a sec.
One pressure, and then subtract that partial pressure from the total pressure to get the last.
Yep.
Okay.
7.768, but it was 8.8.
Oh yeah. Now I didn't actually type this into my calculator. I did use the number from before from the calculator. Again, never said I don't make mistakes. Yeah, so you could have just calculated one of these and then subtracted it from the total pressure to get the other one. And if you wanted to check this, so in this case, the way I did it was I calculated both of these, so I should be able to add those together and get back my total pressure. So that's a check. And that's actually how I realized that I had done this wrong and gotten the wrong number here, because when I looked at 0.264 and point whatever I had there before, I was like, those don't add up to 0.76, 0.769, but now they should. So you'd have these. As your answers. And again, it's not the only way to solve it. I'm not sure if Alex would show you every single way to solve it, but they'll show you one way at least. Any questions about that? This is one of the bolded topics on the list of things for next week's exam. And this is on the recording for today. So it'll be posted maybe even tonight. Technology willing.
Like combustion analysis and
Look, I never tried to trick anybody. I just thought it was an interesting problem because I was looking for a molecule to put in for the combustion analysis. And so I was like, oh, buckyballs are an interesting molecule. And when I Googled it, it was like, it's C60. I'm like, that's weird. It doesn't have any hydrogens or oxygens. Just figure.
yes.
Huh?
Interesting molecules that are electrified.
Easy ones for the test. Oh. Anyways, I don't think there's anything like that. I didn't do anything that I thought was exceptionally interesting.
Comparing to the buckyball,
Exactly. That's what I'm saying.
total mass is 0.
No.
That helps.
Zero ATMs.
Anyways, that's that. Are there any questions about this problem yet? Nope. Good. You can watch it again later. Mistakes and all. I have a lot to get through still, but we could do this one quickly. So to prevent the pressure, prevent the presence of air, noble gases are placed over highly reactive chemicals to act as inert blanketing gases. So if you had like sodium metal and you don't want it to combust when you're working with it, because maybe you need to add some to an experiment, they have a thing called actually, not just noble gases, they'll do this with nitrogen too. Nitrogen's very inert, but you can have a nitrogen or an inert gas glove box, and it's this sealed box that's pressurized with inert gases, and you have to reach, there's like a big window, and you have to reach through with these big rubber gloves to do anything inside. Thankfully, I never had to do any of that. But if you're working with stuff that's really reactive, that could react with air, you would do it in that glove box because it would keep anything out with various noble gases or nitrogen. Now in this one, you've got chemical engineer placing a mixture of these noble gases in a piston cylinder assembly at STP. Calculate the partial pressure of each gas. So there's a long way and there's a short way to calculate this.
I might know the short way and correct me if I'm wrong. Would you take like, we'll start with helium and take like its partial grams and divide it by the total grams of like the whole.
Okay, so can't use grams. We got to convert everything to moles,
Okay, so then you.
but either way we have to do that.
I just thought if you took everything on every single gram and divided it by the partial grams, you would get partial. That's not gonna work.
Everything you said, but replace grams with moles.
Okay, I can do that.
Yeah, so if we take all of these, we do have to calculate, but then we can add all those moles together, get the total moles. We cannot use 22.4 here because it's in grams. And we're not looking for liters. We're looking for the pressure. Now, STP does give us something that's very useful for calculating partial pressures. 1 atm, yeah. Standard temperature and pressure. So 0 degrees C and 1 atm. Specifically here, the 1 atmosphere is the most useful part. So let's quickly convert these into moles. 4.00, 15 grams of neon divided by 20.18. And 35 grams of krypton divided by 83.798. 5.5 divided by 4, 1.375 divided by 20.18, 0.7433, 35 divided by 83. So it's moles. Okay, so the long way to do that, what would the long way be? Yeah, the long way would be to calculate, so take this moles, we have temperature and pressure. I guess we don't have volume, so we'd have to assume a volume. Oh, maybe we can't even do it that way, because we don't have a volume. So this might be the only way to do it. Okay, so the total moles is 2.53, I'm just gonna use 2.536. Yeah. So multiplying by 1 over 2.536 is the same as dividing. By 2.536.
So is there mole fraction going to be the partial pressure because it's not 1 atm?
So the mole fraction, because we're at 1 atmosphere, so all of my mole fractions, once I calculate them all, should add up to 1. That's the total moles. Yeah, so adding these moles together should be 2.536. And then because, again, these are all mole fraction, that means that I multiply each of these by my 1 atmosphere, which is my pressure total. It's going to be exactly the same. That's helium, that's neon, that's krypton. I guess since we have temperature, pressure, and we have moles, you could calculate the volume and then calculate the moles, or then use volume, number of moles, temperature to calculate the pressure of each gas. That's definitely the longest way to do it correctly. Yeah. So if I did PV equals nRT, I need a volume to be able to calculate the pressure of each gas individually. 22.4. Oh, I guess we could use 22.4 here. So 22.41 liters per 1 mole at STP. So I could use my moles, do that to calculate a volume, then use the volume, temperature, number of moles, and calculate a pressure for each gas. Again, there's a reason that we teach this. There's a reason we teach this, because it's the way gases behave, at least ideal gases, and it makes this calculation a lot faster. Just using the idea that all of these gases together make up the full pressure, make up the full number of moles. Yeah.
So I know it would be a rounding error if you did this.
Yeah, it's a rounding error.
Solve for 2, you can get the last thing on.
Oh, if you solve for 2 of these, then I could just say 1 minus those 2. That would give me the pressure of the last one. I don't know if that's easier.
You could do the same with the mole fractions.
Yes. You could also do the same with the mole fractions. Coming up with different ways to solve these problems is a good way to show that you understand it and understand what's going on. Because we don't need to calculate everything, we just need to calculate all but one. And then whatever's left over is the last one. Yeah. As somebody asked what that meant, yeah. That's the molar volume at standard temperature and pressure. Okay. All right, we got to move on. Because this is a quick conceptual. Gas mixture contains an equal number of moles of helium and neon. Total pressure of the mixture is 3 atmospheres. What are the partial pressures of helium and neon? So the key here is equal numbers of moles of helium and neon, which means that it's 50% helium, 50% neon, or the mole fraction of each is 0.5. So half of it has to be helium, the pressure that is. Half the pressure has to be helium, half the pressure has to be neon. So you could do a similar question and say there's 3 gases in equal amounts. So if it was for equal moles of, let's say it's helium, neon, and argon, the total is 3 atmospheres. What's the partial pressure of each? So if I have the same amount of helium, neon, argon, that means that each of the 3 is 1/3 of the total pressure. So take my total pressure divided by the 3, and it's 1 atmosphere each. Okay. Wait, isn't there another slide that's specifically about the pressure of water? No? Okay. Although everybody's done this now, at least knows about it from lab. Whenever you collect gases over water, it's like the easiest way to collect a gas, because I can take the eudiometer, flip it upside down while it's filled with water, and then bubble or create gas inside of the eudiometer and collect that, and it'll be trapped in there because of the water. Now, when you collect something over water, some of that water is always evaporating, and so there's always some vapor pressure of the water contributing to the pressure inside of that air that you collect. And that depends on the temperature of the water. So here they're just telling us at this temperature of 298 K, we've got a partial pressure of 24 torr as my water vapor partial pressure. And really what that means is that pressure of 755 torr is not all coming from the hydrogen being collected. And we need to subtract out this pressure of water. So we take the 755 torr, which is the total, minus the 24 torr. So that's 731 torr. But if we're going to use PV equals nRT, I convert it into atmospheres. Atmosphere. So it's 0.96184. Goes on and on. 0.96184 times 1.55 liters 298.96184 times 1.55 divided by 0.0206, 0.08206 divided by 298, 0.0609610 moles of hydrogen. And some of you came up and asked me, is this number of moles okay in lab for the moles of hydrogen that you collected? If you think about it, this makes a small number of moles makes sense, because if I had 1 mole of gas, that should have approximately a volume of 22.4 liters, whereas your eudiometer could measure up to a maximum of 100 milliliters. So 0.1 liters. So we didn't collect anywhere near 1 mole of gas. It was much less than that. So any partial pressure, water problems, water vapor, you got to subtract out the water vapor to get just the pressure caused by your gas, the one that you're interested in the moles of. Okay, I think I mentioned this. This idea of partial pressures is really important for deep sea diving, because the partial pressure is a better judge of like actually how much oxygen there is, rather than thinking of it in terms of percent. Because if I talk about percentages, breathing air at the surface, we want something like 0.21%. But that's a percent. So around here, it's about 1 atmosphere. So we get about 0.21 atmospheres of oxygen pressure, which again, related directly to the amount of moles. If you go deep sea diving, though, you take this 0.21%, and the air inside of your lungs has to be higher and higher pressure to combat the outside pressure of the water pushing on you. So you can very quickly go from, let's just do it like this, 1 atmosphere times the mole fraction, 0.21, or mole fraction, or the percentage as a proportion, right? That's 0.21 atmospheres. That's fine. But if you go up to 2 atmospheres times 0.21, now that's 0.42 atmospheres of oxygen. And then if we go up to 4 atmospheres, that'd be 0.8. So that would be equivalent to 100% oxygen at the surface. And the deeper you go, the higher the partial pressure of oxygen would rise if you were just using regular oxygen from the surface. Not to mention the other gases that can cause problems. So you can get oxygen toxicity, and of course you can get hypoxia or oxygen starvation if you're not getting enough. You can also get nitrogen narcosis. It's also called rapture of the deep. It's apparently similar to being drunk, alcohol intoxication. But it's because you get too much nitrogen in your lungs and it's dissolving into your blood. And then that nitrogen in your blood can cause psychological symptoms. Same with oxygen. Oh, more mole fractions. Oh, see, here's the collecting gases over water. This is a pretty quick problem, so we do this one. A diver breathes a Heliox mixture. So Heliox is oxygen and helium. Also makes you sound like a member of Alvin and the Chipmunks, just like regular helium does. But it doesn't dissolve in your blood and have the same problems that nitrogen does to a point. If you get too high a partial pressure of helium, I think it also causes issues. So diver breathes Heliox mixture with a mole fraction of 0.050. So what must the total pressure be for the partial pressure of oxygen to be 0.21 atmospheres? Sorry, so we'd use the mole fraction equation here, meaning the partial pressure of oxygen is equal to the mole fraction of oxygen times the pressure total. And here we have our mole fraction of oxygen. We have the partial pressure of oxygen that we want, but we need trying to find the total pressure. Which is basically saying if I'm going to dive down to however many meters and the pressure is going to be super high, what do I have to adjust to? Or how will that change the oxygen? So 0.21 atmospheres equals 0.050 times pressure total. And so you just take 0.21 atmospheres divided by that mole fraction. That should be 4.2 atmospheres is the pressure total. So really that one comes down to remembering that this equation incorporates two of those three things and then rearranging it. No, I'm going to give you a bunch of formulas. I don't think there's any formulas that you have to memorize. So this is where I was talking about gas collecting over water. We're going to do something similar actually tonight's lab, Friday's lab, except it'll be collecting oxygen. So this is another way to collect those gases though. So instead of the eudiometer, we could have done something like this where we collect the water inside of an inverted beaker. The thing is, a eudiometer is designed to be able to measure the volume of that gas. This doesn't give us a way to measure that as readily. It just would let us trap it. So that partial pressure of water is the vapor pressure. You have a chart and you basically say, what temperature is my water at, or what temperature is my whole setup at? And then I find the vapor pressure from the chart and subtract it out. We did one of those. Sorry, I gotta skip these. These slides are taking longer than I wanted them to. Okay. So we've talked about, at this point, stoichiometry problems where we start with grams. We calculate grams of other things. Talked about solutions where you start with a volume of a solution and molarity. And again, the goal there is to first calculate moles. And then you can calculate the moles of something else in a chemical reaction. We could do the same thing for gases. So when we're doing these stoichiometric calculations, most of the time you've got a pressure and a volume and a temperature for some reaction of some gas, and then we can calculate the number of moles. Or you can rearrange that to find the volume of the gas depending on what the question's asking for. The easiest version of this problem happens at STP, because at STP, it's using molar mass, except now we've got one number for everything. So for at STP, and I might not always say STP, it might say 0 degrees Celsius, 1 atmosphere of pressure. You should read that as STP, and that you could use this 22.4 liters per 1 mole of any gas, any ideal gas. So again, the plan, the conceptual plan is the same as converting mass to amount of moles, and then using the mole ratio from a balanced chemical equation to find the moles of another compound or another species in the reaction, and then finding the mass. Now we're just using pressure, temperature, and volume, pressure, volume, temperature of a gas to find the number of moles. Again, mole ratio. Then we can find the moles of a different species in a reaction and convert that to pressure, volume, or temperature of gas B. It's usually volume that you end up trying to find. Pressure and temperature are usually given because it's going to be set for the whole reaction, basically. Could also use partial pressures. So for this reaction, we got 4.58 liters of oxygen was formed at a pressure of 745 millimeters of mercury, at a temperature of 308 Kelvin. How many grams of silver oxide decomposed? The question always with the stoichiometry problem, and actually, how do we know it's a stoichiometry problem? Aside from the fact that I literally just talked about it. One hint is that they give you a balanced equation.
Yes.
There's another one. They're asking about, yeah, I think that could be one too. How many grams of this decomposed? What I'm looking for is that they give us two different things in this reaction that they give us numbers for. Basically, they say, here's an amount of oxygen, liters, we've got a pressure and temperature, find grams of silver oxide. The only way I can do that is if I have a balanced chemical equation that relates those two amounts. Yes, it's a decomposition reaction. Yes, having a balanced chemical equation is a hint at that. But stoichiometry is always converting from one compound to another compound through some chemical reaction. The first question is always, what can I calculate the moles of?
And the conversion factor is actually
Huh?
like if you're given a conversion factor, and you derive that from the equation.
Which conversion factor are you talking about here? Just like the balanced chemical equation? Yeah, like any relationship between these coefficients is going to be a conversion factor to get from oxygen to silver oxide in this case. Did that answer your question? All right. To do that though, these are all related by moles. So I have to be able to calculate moles of something. And what can I calculate moles of? Yeah, oxygen. Right? I can't calculate the grams of silver oxide. I can't calculate the moles of silver oxide because I don't know what the grams is. I'm also not given a volume of silver oxide. So there's no way that I can calculate anything about silver oxide right now. Obviously, we can get there, but given a volume of oxygen, a pressure and a temperature, you do PV over RT equals N. Just rearranging PV equals nRT. And then this pressure needs to be converted. 6. So 0.9826 times 4.58 liters divided by 0.0 times 308 Kelvin. So just calculating the number of moles of oxygen first. So that's 0.1776. We go to 339. Okay, the reason we wanted to, and this is like one of the most common mistakes that I'll see, is you do this, you get moles of oxygen, and you're like, cool, and then you go and convert it, somebody will go and convert it into grams of oxygen. Grams of oxygen doesn't really help us. We wanted to get to moles because that's the relationship in the balanced chemical equation. Yeah, so we want to get to silver oxide. So now I say, okay, I've got this number of moles of oxygen. So what's my ratio between oxygen and silver oxide? 1 mole of O2 and 2 moles of silver oxide. Great, so that's going to give me moles of silver oxide because moles of oxygen cancel out. Yeah, then we multiply by the molar mass of silver oxide. So that's 231.74 grams per 1 mole. So 0.1776339 times 2 times 231.74, 82.3 grams. So there's usually going to be part of the equation where you're either calculating moles so that you can plug it into our regular railroad track setup, or this question could be asked in reverse. I could say 30 grams of silver oxide decomposes. How much gas, oxygen gas, would be produced at a pressure of 1 atmosphere and 273.15 Kelvin? And then we would go the other way, and once we got to the end, we'd get a moles of oxygen and convert that into volume. Yeah, this is the molar mass of silver oxide. Any other questions? Nope. Okay. Oh, okay, so this one's nice. How many liters of oxygen at STP are required to form 10.5 grams of water? So again, how do I know that this is a stoichiometry problem? Aside from the obvious stoichiometry. Yeah, it's asking for how many liters of oxygen are required to form this many grams of water. So 2 different compounds. To do that, I need a balanced chemical equation, which was given, which is another hint. And the only thing we can calculate moles with, or moles of, is the 10.5 grams of water. H2O. And then the molar mass of water. And then the mole ratio. We want oxygen, so 1 mole of O2. Now, at this point, this is actually what I was just talking about, doing that other problem the other direction. This would give me moles of oxygen. And then I could plug that into PV equals nRT and calculate the volume. Or, because it's at STP, I could multiply by 22.4 liters per 1 mole for any gas at STP. So because this is at STP, I can do 22.41 liters per 1 mole. And that'll give me the volume of oxygen. So 6.5 liters of oxygen. Yes. But what would my pressure and temperature be? So we could do this without the 22.41. Yeah, the standard temperature would be 273.15 Kelvin or 0 degrees C, but we need it in Kelvin, so might as well do Kelvin. The pressure, 1 atmosphere. And it is 1 atmosphere exactly. So that 1 ATM would not affect our calculations or sig figs. 22.41 is not exact. It keeps going. Yeah. Okay. So we talked about kinetic molecular theory some, and so this is just a recap. In the textbook, they talk about kinetic molecular theory at the end, but I like to tie it in with all the simple gas laws and everything else. So, right, it's talking about, oh, right, because I moved those slides at the beginning. This idea of kinetic molecular theory, again, is that we have all of our particles, or our gases are made up of particles in constant motion. They're bouncing off of things without losing any energy, and the particles themselves don't take up any space. And this is the best theory that predicts all of these behaviors about gases. So the reason that R exists as a constant is because all of our gases behave the same way as these point particles bouncing around inside of a container. And so we're just changing properties of those gases when we heat them up, when we increase pressure, when we decrease pressure. They all are affected the same. So the temperature of a gas is related to the kinetic energy of those particles. Right? If I increase the temperature, I'm giving more kinetic energy to all of those particles as they're bouncing around. That's why pressure increases, because they've got more energy, they hit the walls harder, have more kinetic energy, so it creates more pressure. Now, kinetic energy is this physics equation, 1/2 mass times velocity squared. So the mass of the particles is not always the same. Right? I can go to the periodic table and we could look at just even the noble gases, like neon's 20, argon's 39, almost 40, 83, 131. Iodine is a gas would be 126, right? So in a gas at the same temperature, these would all have the same average kinetic energy. But because xenon's bigger, it would be moving slower. So like a semi-truck, for a semi-truck and a motorcycle to have the same kinetic energy, the motorcycle would have to be ripping. And the truck would have to be going relatively slow to have the same kinetic energy. So the larger the particle, the slower it moves. The smaller the particle, the faster it moves. But at the same temperature, it's the same kinetic energy. Because that's a product of mass and volume. So this is just the equation to calculate for a gas at a specific temperature. Again, you don't need to memorize the equation. You don't even need to remember. I actually don't think you need to know. You need to know the concept of this for the test, not necessarily how to do a calculation for it. I don't think you even need it for Alex. The point of this, though, is this is the root mean square velocity. So mean here being the statistical version of mean, not that they're like angry or that they like to kick small animals or something. They're not mean. It's the average speed of all the particles. They're not all going the same speed. I think I showed you that simulation. Some of them are going really slow, some of them are going really fast. But that distribution, how many are going fast and how many are going slow, changes as you change the temperature. Increasing the temperature means more of them are going fast. So this is just to say that the temperature affects the speed, the molar mass affects the speed, and we're talking about the average speed of all the particles of that gas. This part is relevant for the Alex homework. There's a question that asks you about these distributions and to compare things. Ultimately, it just comes down to velocity. So as particles start to move faster, or as they get lighter, their distributions do two things. Actually, I guess I should say they do three things. As it goes faster, the peak of that distribution moves to faster and faster velocities. Also, the width of it gets wider, and it gets flatter. So basically, as I increase the speed or the temperature of a gas, everything starts to go faster. We start to get a wider and wider distribution, meaning that we have fewer particles that are going the same speed and more particles that are spread out across all of the possible speeds. I don't know if you guys know there's a helium shortage. Yeah, there's a helium shortage because every time helium is only made by radioactive things decaying inside the Earth. So there are certain places where there are pockets of helium, but helium up towards the high end of its molecular velocities at like average temperatures on Earth is fast enough to escape Earth. So there's some amount of helium particles that are going fast enough, they've got the escape velocity to just leave Earth and go out into space. So as Earth is hurtling along, we're losing hydrogen, but there's so much hydrogen. But we're also losing this helium, just shedding it into space. It'll be a problem eventually. Huh? Yeah, that's why every time I see party balloons that have like helium in them, I'm like, ah, that could have been used in a GC. That could have been used for scientific instrumentation or cooling supermagnets, superconductors. All these nerdy reasons. So this is what I was talking about. As the temperature of a gas increases, the velocity distribution shifts higher, and then the distribution flattens and spreads out. So in this one at 273, like all of my gas particles have this speed, the speeds between here and here. Right, so they're all in this range of speed. There's a few faster, there's a few lower, but that widens. So at 1,000 now, there's a lot more options for speeds for these gas particles. And as you continue to go faster and faster, you'll just have some particles at every possible speed along that curve. Anything that increases velocity of the particles, meaning if I'm talking about lighter particles compared to heavier particles, if I'm talking about hotter particles, gas particles, compared to colder ones, anything that increases the velocity causes it to spread out and flatten. Oh, all right. It's 6:24, so we're gonna have to call it.